You know, everything around us, I mean everything, is made up of elements. They're the basic building blocks of our world. But here's the thing, these elements pretty much fall into two very different families, metals and nonmetals. So how can you tell them apart? Well, today we're going to solve that elemental mystery.
Okay, imagine this. You're like a detective, and you've just stumbled upon some strange, unknown solid. Your mission, should you choose to accept it, is to figure out what it is. Is it a metal or a nonmetal? To crack this case, you've got to know what clues to look for.
And just like any good detective, we're going to start by gathering clues. We'll build a profile for our first suspect by looking at all its classic properties.
Our first suspect is a big one. It's a whole family of elements we see literally every single day, from the coins in your pocket to the car you drive. So let's get into it and build the profile for metals.
So what is it that makes a metal, well, a metal? We're going to ask a few simple questions that'll help us uncover its true identity.
The very first clue is the most obvious one. It's totally visual. Just look at it. What do you see? Does it catch the light? Does it have that certain sparkle?
Oh yeah, that distinctive shine is one of the biggest giveaways. In science, we call that property luster. It's the first big checkmark on our metal profile. Just picture a polished piece of silver or a brand new copper pipe. That's luster in action. Okay, clue number 2. Let's get a little more hands-on. What happens if you take a hammer to our mystery substance? Is it going to shatter into a million little pieces?
Well, if it's a metal, it's definitely not going to shatter. Instead, it'll just bend and change shape. This reveals two really key properties. Metals are malleable, which means you can hammer them into thin sheets. Think aluminum foil. And they're also ductile, which means you can stretch them into thin wires, which is perfect for all our electrical wiring.
All right, for our final clue, let's see how it deals with energy. What happens if you hook it up to a battery and a light bulb? Will electricity flow? And what about heat? What does it feel like when you touch it?
Yes, and this is a huge one. Metals are fantastic conductors. The reason why is that their atoms have these electrons that can just move around freely. It's like a sea of electrons that lets electricity and heat travel through the material super easily. That's also why a metal spoon feels cold when you touch it. It's not actually colder than the room. It's just pulling the heat away from your hand really, really fast. That's conductivity. So let's recap the metal profile. They're shiny, they can be bent and shaped without breaking, they're great conductors of heat and electricity, and they're usually pretty strong and dense. Oh, and they often make a nice ringing sound when you strike them. We call that being sonorous. Case closed on metals. Now let's shift gears and look at our other main suspect, the nonmetals. We're going to run them through the exact same checklist of clues and see how their profile stacks up.
First up, back to the visual test. When you look at a nonmetal, say a piece of sulfur or a lump of charcoal, does it have that same metallic shine?
Nope, not at all. The difference is pretty stark, actually. Nonmetals are usually just dull. They don't have that reflective luster. Their surfaces tend to absorb light instead of bouncing it back at you.
Okay, next up, let's talk about strength. What happens if we try that hammer test again? Or even simpler, what if you just drop a solid piece of it? Does it bend or dent or what?
It's the complete opposite of a metal. Solid nonmetals are brittle. Instead of bending, they just break. Think about a piece of chalk. If you try to bend it, it just snaps right in two. That's what being brittle is all about.
So the nonmetal profile is pretty much a perfect opposite. They're dull, they're brittle if they're solid, and they are terrible conductors of heat and electricity. Actually, because they're such poor conductors, they make excellent insulators. That's why we have plastic coatings on electrical wires. They're also generally less dense and, interestingly, can be solids, liquids, or even gases at room temperature.
Okay, we've built our two profiles. Now for the fun part. Let's bring our two suspects into the interrogation room, put them side by side, and compare the evidence directly. And when you lay it all out side by side like this, the differences are just crystal clear. Shiny versus dull, malleable versus brittle, conductor versus poor conductor. It's really a tale of opposites, isn't it? This comparison is the key to solving our elemental mystery. It lets you identify pretty much any substance you find. Almost. Because, just when you think you've got it all figured out, science loves to throw in a plot twist. It turns out, not every element plays by the rules we've just laid out.
So, here's the million-dollar question.
Are these profiles 100% foolproof, or are there some elements that just like to live in that gray area, right between our two neat and tidy categories?
Okay, so take a look at graphite. It's just a form of carbon, which is firmly in the non-metal camp. And yeah, it's brittle, just like we'd expect, but it also conducts electricity, which totally breaks one of the biggest non-metal rules. This unique property is exactly why we use it in things like batteries and electronics.
And then you've got silicon, the element at the heart of our entire digital world. It's a non-metal through and through, but it has that distinct, shiny luster of a metal. It completely defies its category. It's these fascinating exceptions that show us where the simple rules end and, where the deeper chemistry really begins.
And this really gets at a much bigger idea, doesn't it? We create these categories, like metal and non-metal, to try and make sense of the world. But nature is always more complex, more messy, and way more interesting than our simple rules suggest. It just makes you wonder, what other fundamental rules of science are out there, just waiting for the right exception to come along and change everything we think we know?